Okay. Okay. So, right off the bat, there's a typo with your slides. You need to change that chapter 10 to 11. And actually, this unit of material is 4 chapters again. It's 11, 12, 13, and 14. And when we get to chapter 14, actually it says chapter 13, so you're going to have to change that to a 14. Obviously, probably you already figured this out. What happened is the textbook that I enjoy using inserted a chapter. They inserted the chapter on extra solar planets, so that's kind of messed me up. But again, kind of like we've done before, I'm not going to spend a whole lot of time with these, okay? I thought the video that we watched the other day, and I think I've posted the video to the Twitter feed. If I haven't, I will. All that stuff, the universe, especially the early season, those documentaries you can get off of YouTube. But one of the things, the guy kept coming back. He was on the beach. I love these settings, right? He was on the beach and he had a little fire, and he's like, dude, this can't be what's fueling our sun, okay? Because it would run out in 10,000 years if basically ordinary burning, like you have a fire. And then the next one says basically we know that actually you can get heat if you take something that's this big and make it smaller, okay? Because that's what you're converting gravitational potential energy into thermal energy. And that would only give us 25 million years. Now remember the date, one of the dates in this class I want you to get under your belt is the 4.6 or 4.55 billion with a B years. And so that's what we're looking at with regard to how old our sun is, 4.6 billion years old. So actually, if we go with the nuclear fusion route, which was the answer to today's quiz question, okay, then you do go ahead and it makes sense with regard to timing. So if we are about 4.6, are you guys about done? Or?
Yeah,
okay.
Actually I had it written down and I was like, I don't know, but it was right.
Okay, good. Okay, so if you take 4.6 billion years, okay, 4.6 round it to 5, so 5 with a B. So here's the deal. Our sun can do what it's doing when it started for about 10 billion years, so it's about halfway through. Okay, and I think you remember in the documentary they talked about the next step for our star. It won't blow up because it's not big enough. We'll talk about stars that do blow up, but it will actually expand too. And I liked that basically it said the Earth might kind of go out a little bit, but it'll still be kind of crispy. Okay. So our sun is actually chugging away right now. And for this slide, I'm actually going to tell you that the sun isn't swelling, nor is the sun shrinking. But what the sun is doing is it's a very dynamic little beastie entity. Okay, do you see like the green and the orange down here? Okay, the green looks like it's going inwards. That's actually gravity. Okay, and the little orange ones, the little arrows going outward, that actually is kind of outward pressure of the sun as it creates energy in its core. Only in its core do we have this nuclear fusion going on. So basically we have it outward and inward. And the cool thing, anytime you hear the word equilibrium, okay, that means something is actually kind of doing this and something else is doing that, kind of opposites. And those are the two opposites we have at equilibrium. So gravitational equilibrium is the state that our sun is in. Okay, notice if gravity was losing out, okay, if gravity was winning, it would shrink down. If gravity was losing out, it would swell up. So actually when we talk about stars kind of going to the different stages, something's giving, something's happening there. All right. So I kind of said that. What else we got? We will be talking a little more in my slides exactly what we saw in the documentary about the energy created for nuclear fusion working its way out. I just think that is so cool. Okay. Now, one of the things, you see these little squiggles? This is kind of cool because when we talked about the greenhouse effect, we had like a little squiggle coming down through the Earth's atmosphere. There's a squiggle, okay? Energy from the sun radiating in all directions, including the direction of the Earth. The cool thing is basically the squiggles, the energy leaving the sun, is about how much energy is created. So it's kind of nice. That makes sense, okay? So when we talk about other stars, we're going to kind of be comparing other stars to the sun. So with regard to the sun is just kind of like a typical star. And I think you might have heard it in the documentary, it's like Goldilocks, where, Goldilocks wants to be right in the middle. Okay, that's kind of what our star is. You see some statistics there with regard to the Earth. An important thing about any star, including the sun, is basically how much squiggles it's giving off. Okay, that's what we call its luminosity. When you pick up a light bulb to go ahead and put it in a light fixture, you're like, oh, what's the watts, right? Okay, what's the luminosity of the light bulb? Okay, that's kind of what we are with regard to sun. Now remember, whenever you see a couple numbers up here packed up in scientific notation. And this semester I kind of briefly reminded you what that means. Okay, so 3.8 times 10 to the 26th, basically you take this decimal that's right here and you move it over there 26 places. Okay, so it's a big number. What else about the sun? Well, the sun's mostly hydrogen, 28% helium. Do you think the helium's increasing and the hydrogen's decreasing? Yes, totally. There is iron associated with our sun. We've seen it in the spectra. That's the reason we know that actually it's a second generation star. How fast does it spin? So remember the video talked about differential rotation? So actually this is talking about differential rotation right here. Differential. You get different from differential rotation. Remember they talked about, actually this is when we talked about sunspots, but basically at the equator it goes faster than at the poles. What else about our sun? And this again is things we're going to talk about for other stars. We actually have seen this value. Remember K is Kelvin temperature scale. And so we actually looked at a radiation curve, and basically we said that how hot something is, you can get a fix on, if you do wavelength versus intensity, you can get a fix on where the peak is, and if it's cooler, it'll be kind of more reddish, and if it's hotter, it'll be more bluish, okay? And we actually had a radiation curve of the sun, and it showed us that that radiation curve was consistent with an object that's about 5,800 Kelvin, or 6,000 Kelvin. Now that's the surface temperature of the sun, okay? The core is a lot hotter. All right, so what else about the sun? Well, we've run into solar wind before, okay? Mars, poor Mars, lost its atmosphere because of solar wind, right? The Earth's magnetosphere protects us from charged particles in the solar wind. Here's a cool term, I think. The term heliosphere, it's like basically, okay, so here's our sun, okay, and here's the planets. And the sun has this solar wind in all directions, including the plane of the ecliptic and, I guess, north and south. So basically, it creates this bubble of, which eventually peters out, okay, and that's what we call the heliosphere. And so I've heard people discuss, like, if we're going to get organisms or anything from other stars, basically it has to swim upstream from that solar wind. It's something to think about. It's kind of a way of cleansing, it's a positive pressure, kind of keeping our solar system pure from things that don't have momentum to come into our solar system. All right, so the layers of the sun's atmosphere. Now, so the layers of the sun's atmosphere, and they did talk about this. I remember that they spent a little bit of time talking about how this crazy corona, okay, and here is the corona. So the corona is the outer layer. It actually is the hottest. Remember how he had the fire and he had the thermometer, he's like, okay, so it's hot here, and if I get farther away from fire, it's going to cool down. Well, as you get farther from the core of the sun into the corona, it's very hot, and he kind of explained how that maybe would be. The photosphere, I've heard it kind of likened, the photosphere is kind of what this slide says, the surface of the sun. So is it the sun's atmosphere? I don't know. It goes photosphere, chromosphere, corona. And okay, so that was the outer layers. What about the inner layers? Well, the core is where you have the nuclear fusion going on, okay, that you guys told me today. And we're going to take a look at that nuclear fusion, kind of like the video did. And it needs to be very hot and very dense. Those two conditions will give you nuclear fusion. So beyond the core, we have these two layers of the sun. Beyond the core, first we run into the radiation zone. And I have a figure from your textbook coming up, but remember they called it the Wander Walker. It's the walking, I don't know, but it's just kind of a wandering sort of. This right here in the radiation zone, this can take like up to 170,000 years or something. It takes a long time for a little photon of energy that's created in the core to work out through the radiation zone. And then it gets to the convection zone, and I like it when we get to a topic we've talked about convection, convection cells. What is that? Basically, warm plasma from the sun rises, it cools down, then it sinks. Okay, these little convection cells. So it goes faster there. And then when it gets to the photosphere, ding, speed of light in all directions. So I just think that is amazing that it can take hundreds of thousands of years, that little energy. I just think it's so cool. Okay, so nuclear fusion. Now this is not nuclear fusion. There's two types of nuclear reactions, and they both give you energy. This type of nuclear reaction is what we see in our power plants. Okay, what we see in our bombs, quite frankly. Uranium is great at doing this. Okay, what is this? Basically, that kind of red and black thing is showing you protons and neutrons in the center of an atom, because we talked about how an atom is constructed. Those are protons and neutrons, and basically the nucleus is splitting. What are the electrons doing? I don't know, whatever they want to do. Okay, but we're just talking about the nucleus of an atom splitting. That's called nuclear fission, and it releases a lot of energy. Nuclear fusion is maybe what you guys put down on your quizzes. So nuclear fusion is where it's fusing, or two light things are fused together. And when I say light things, I mean the center of atoms are fused together. Okay, in the case of our sun, it's taking the simplest hydrogen, fusing together to get helium. When we switch gears and start talking about other stars, we're going to see that actually conditions in the core can ramp up. We can get higher temperatures, higher pressures, and actually we can take helium, ram them together, and get something heavier, like carbon. Okay? So that's nuclear fusion. So let's take a look specifically at the fusion in our sun's core. Okay? And I probably won't get too picky, but I'll kind of try to summarize it. The video, I think, kind of had an animated version of this that we saw on Monday, where basically kind of this top one up here, if I call this A and this B, A and B, A is an unsuccessful collision. So what it's saying here is, this is scenario A, and this could be scenario B. Okay, what is A? Basically the nuclei, or protons, nuclei, are basically kind of colliding, but they go away. Down here for B, if you have them going fast enough, and if you have it high enough pressure, then you will actually have a successful collision, and you'll create a heavier nuclei. So in the context of what we've been talking about down here, this would be helium atom, and these would actually be two hydrogen atoms. Kind of like that. The nuclei of hydrogen anyway, which is just a proton. Okay, but that can only happen at high speeds, high temps, and high pressures. So we've been kind of talking like it's basically you take two hydrogen and you get one helium. And I'm going to kind of correct myself here. Okay, it's just a little more complicated than that. You actually end up taking 4 hydrogen and making 1 helium. And the cool thing is that each hydrogen is just P stands for proton. Each hydrogen is just a proton. And so what's going to happen is 2 of those protons are going to have to be converted to neutrons. Yep. And a lot of energy is created. So Einstein said that you can convert energy to matter. I'll kind of highlight this on that slide. This whole classic, this thing, E is equal to mc squared. Looks like it ought to be on a t-shirt. Okay. So what Einstein says is that you can convert matter, that's the M, matter, a certain amount of mass of matter, directly into energy. You can. And so what's done in the nuclear reaction in the cores of stars, our star in particular, basically, is if you compare this mass, I'll call this M1, I'll call this M2. If I compare the mass of my 4 protons, which are 4 hydrogen nuclei, plus the mass of my nucleus of 1 helium atom, I'm going to say M2 is less than, I should put it this way, I'll put it this way, M1 is greater than M2. M1 is greater than M2. Like, how does that happen? Because mass has to be conserved. But in this case, with nuclear fusion, it actually has to do with binding energy is released. Okay. All right, so how much energy are we talking about? Well, each second, 600 million tons of hydrogen are converted into a slightly less mass of helium. So there's your mass loss. And you can take that, 4 million tons of matter and kind of do the math. E is equal to mc squared. Take that 4 million tons, convert it in for the m term. C is the speed of light, and see how much energy you get. A lot. So here's a figure, I think, from your textbook. Sometimes I grab figures from other places, but basically kind of show you the whole nuclear fusion inside our star. So right here, that's kind of a summary of what I just said. Notice we have our 4 protons combining together to get our, this is the nucleus of a helium atom. So we have 4 hydrogens to get one helium. Now notice that also, I like this nice concise thing. It's kind of a summary of these other 3 blocks. What else is given off, if you're a picture person, are these things. Okay, the white things are neutrinos, and the red things are positrons. So basically, you put 4 protons in, and what you get out is a helium nucleus, 2 gamma rays, and actually those 2 gamma rays, that's going to be your energy. Gamma rays, energy. And what else do you get out? Those other particles I showed you, the little white ones, the little pink ones a minute ago. 2 positrons and 2 neutrinos, yep. The last slide in this lecture actually is going to look at neutrinos. So one of the things about science, they're pretty good. I think they try to keep themselves honest. And they're like, all right, if this is what's happening, okay, we should be able to see a bunch of neutrinos. Okay, because this process is happening a lot in the sun. So where are the neutrinos? And the problem with neutrinos is it's a little subatomic, it's a piece of particle that's like smaller than an electron, and it basically goes right through matter. So we actually have a figure from your textbook that is a gizmo that tries to detect the presence of neutrinos. So again, what you start with is more mass than what you end with. How much less mass? How much more mass? 0.7%. All right. So this is where I kind of need to backtrack a little bit. Remember we talked about gravitational equilibrium? That was kind of the whole sun thing is not expanding because of the energy it's putting out, nor is it contracting because of gravity. It's like a balance. Well, this kind of talks you through, actually, there can be a little bit of wiggle in the volume of the sun, and it kind of resets itself. So if you start in right here, you start with this one right here. Okay, this says a slightly cooler temperature. Okay, well, if the temperature gets a little bit cooler, then actually what's going to happen is, I don't know if you can see this line right here. I've got green on top of green. Okay, if the temperatures cool down, then basically the rate of nuclear fusion is going to cool down, so it's going to have less pushing out. If that's the case, you're going to basically, the inward thing is going to kick in. What's the inward? That's just gravity. What does that mean for the star? It's going to get smaller, and we're going to see this in other stars. As it gets smaller, what happens? Basically, it's converting potential gravitational energy into thermal energy. Bottom line, it gets hotter as it shrinks. So here now we have it getting hotter. What happens when it gets hotter, and they don't really show this correctly, I don't think, As it gets hotter, then that fusion rate increases. So we have a kind of a temporary, I would put a longer line there, kind of a temporary swelling. Okay, so it kind of goes back and forth. And the other does kind of just the opposite. It says, okay, what if instead of cooling down, it got a little bit warmer? Well, if it gets a little bit warmer, then actually it's going to expand, and it's going to cool down, and it's going to, so it kind of has its own little bit of wiggle room. I'll go ahead and throw a term at you that we're going to be talking about in this unit, and it's called main sequence stage. Main sequence stage. That's just basically an important, you know how like when people are, we talk about the stages of life for people. We talk about, if they're, baby or infants, and then they are, adolescents, teenagers, young adults, middle-aged, elderly, okay? So we do that with stars, okay? So basically, a time in a star's life is called main sequence stage. So the random walk, that was the term I was trying to find. I think that's what they use in the video, the random walk. From the core through to the radiative zone takes like forever, okay? But basically they're showing the gamma rays, that energy that's released during nuclear fusion, wind itself out. And I like the video because basically they said, how does it work with that in the radiation zone? Well, basically with contact. It hits this one, it hits this one, it hits this one. And sometimes it goes backwards probably a little bit, it wiggles sideways, but ultimately tries to kind of go to the photosphere of the sun. So beyond the radiative zone, we have the convection zone. And the way I think of it is kind of the convection zone kind of leads into this kind of cool feature on the sun we call granules. And they make me itch. If I could animate this, okay, and I've seen animated, this is like the surface of the sun, this is like the photosphere of the sun, and here we have the chromosphere and corona, and then underneath there we have the convection zone and the radiative zone of the core. This actually, they're kind of like, they go like this. They're about the size of Texas, okay? I know. So underneath each one of those, it looks like kind of like a honeycomb. Underneath each one of those is one of this, okay? And what is that? Basically, it doesn't look like kind of almost, I guess, a pair of convection cells coming up with each granule, okay? Warm plasma from the core of the sun is rising, it cools, okay, it gets more dense, and then it sinks. Okay, so that's kind of what's going on. Those are granules. All right. So physicists, actually there's almost two groups of physicists. There's like the experimental physicists, and then there are the theoretical physicists, okay? And they actually talk across, okay? But the theoretical physicists rely on the experimental physicists to kind of, but anyway, what the people who don't collect data, what they can do actually is kind of do their math and look at the physics of it, and they can understand what's happening in the sun's interior just by understanding the nature of matter, and in this case the nature of nuclear fusion. But what the experimental astrophysicists would be doing is be gathering data from the sun. And the sun is a very busy place. I don't think I have a slide this semester, but you know how Mars is a very busy place? The sun is a very busy place. We've got telescopes just looking at the sun. And the video alluded to protecting our assets, not our assets, but protecting our assets, okay? And the reason we're so interested in what the sun's going to do is it can be very bad. It can actually kind of be active and kind of compromise our assets. So how do we know what's going on in the sun? Well, it's kind of like, remember we said, how do we know what's in the interior of the Earth? You're like, I have never been there, okay. But one of the things that we can do is seismology, kind of look at waves as they travel through the Earth. The same thing with the sun. We're looking at waves, and actually I think the video kind of addressed this. Remember it's talked about sunquakes, right? That's kind of where this is going. Neutrinos, you basically get 2 particles of neutrino for every successful 4 protons or 4 hydrogen that make 1 helium. And so looking for those neutrinos has been tough. Okay. And then this is my little gizmo to show you them looking for neutrinos. So and this talks about, this is actually buried deep beneath the Earth's surface, because I guess maybe we're counting on the Earth, well, we don't want anything to interfere with it. It's filled with a fluid that is hopefully going to be sensitive in statistics to a certain extent to neutrinos, okay? So neutrinos basically go through matter, but they can, and I think it's like a chlorinated compound. So I thought that was my last slide, but I guess it's not. Well, we're getting there. So one of the things that they talked about on the video is this idea of an active sun and a quiet sun. So an active sun gets everybody all freaked out and all excited. A quiet sun, you're just probably kind of ramping up, gearing up your science for when the sun is going to be active again. So it's an 11-year cycle. So it peaks about every 11 years, In the movie, The Day After Tomorrow, where, I don't know if you're familiar with it, but basically it was a crazy sort of weather change. It was like, it would have been climate, but was on a very short time scale. So one of the things they looked at was what's the activity of the sun, and of course that wasn't it. So if the sun is active, if it's in active mode, we have several signs of that. And so actually I have kind of, the rest of the slide talks about what are the signs of an active sun. So can you see in this figure right here, can you see the granules we just looked at? Okay, about the size of Texas, like these little things. I'm not pointing at it right. Don't point at the big blob. Those little dots, yeah. Those are actually granules on the photosphere. And then underneath that would be the convection zone of the sun. So if they're the size of Texas, okay, what's that the size of? So I think the video said it could be like the size of Earth, okay? So that is a sunspot, and that hopefully when we do our sun lab, we will see those sunspots, okay? So that's a sign of an active sun. So this down here, actually, I've seen it. This is actually the amount of the sun covered by sunspots. So sunspots is one way to track this solar activity. Other things that are probably more interesting than sunspots, remember she talked about that rubber band that would break and it would like that? So here you see actually material lifting off the sun, that if that material, if gravity loses hold of that material, then it is, and if the Earth is over here, we're in trouble, okay? So basically, when a whole chunk of material comes from the sun, we call that a coronal mass ejection, affectionately called a CME. So here, coronal mass ejection is a CME. What else? Well, we have prominences, filaments, coronal holes, sunspot groups, solar flares. This picture down here, was weird. This picture down here is the coronal holes. Does that not look scary or what? Looks like they're ready for Halloween, right? Actually, I don't know what year it was, but NASA floated one of these around that was a photograph of the sun, and it had like a face, jack-o'-lantern. But this actually is taken in, not in the visible region of the electromagnetic spectrum. It's in X-rays. So we kind of talked about how you can kind of finesse the information coming from, in this case, the sun, by looking at different wavelengths. All right, so what's up with the whole 11-year cycle? I liken it to playing Twister. Okay, so right here, down here, these little black blemishes, those would be sunspots. So a pair of sunspots, and actually the video talked about this too, a pair of sunspots can be like a little conduit for the sun's magnetic field to go up and out. So you know, like, we're so like the Earth has a magnetic north and a magnetic south, right? Well, what if on the surface of the sun within, well, you figure if that's the size of the Earth, there's a fair bit of distance, okay? But within a short amount of distance, kind of, relatively speaking, on the sun, you have a north and a south pole. So you have magnetic field lines going from one to the other. And that's what happens. which would be fine, but as the sun rotates, okay, it becomes especially interesting. So this is where the gal talked about, these are sunspots, these black things are sunspots, and this would be the magnetic field. You can actually have material trapped here so you can see it, because otherwise you can't see the magnetic field. Okay, there's plasma being trapped there. This plasma, sometimes it can fall back down, but sometimes it can actually burp and send material towards, swinging towards the earth. So down there in the corner, I like what your textbook has done, and it really reminds me of playing Twister. Like where you start out at the beginning of the game and you're like, oh, that's normal, I can do that, I can put my hands here and my feet there, no problem. But then they start to spin and you're like, and everybody has to put their hands somewhere else and their whatever somewhere else, okay? And you get all wound up and then you all fall down. That's exactly what happens on the sun, okay? And what's twisting it is this differential rotation. It goes faster, the sun rotates, literally rotates faster at the equator than it does at the poles. Okay. So, I think that's it. So this chapter will be due on Friday.